if we look at what we've learned so far, we're going to find some interesting things. Let's look at momentum. This is where this all comes from. Momentum, we use the symbol P, and what we can say is P is equal to energy over C. What we've basically said is E equals mc squared there, haven't we? E equals mc squared. mv, mv squared equals E, or mc squared. So I know this is playing around with equations in a way which we've been a little bit careless, but let's just see where it goes. It's amazing where it goes. So E equals HF, that one we learned out for quantization of photons. So basically at this stage we could relate these back and say HF equals PC, right? What is that going to tell us? HF equals PC. So that means, and if we say that F over C, let's just relate that back to F over C. So F over C, this one here, F over C must equal P over H. But F over C is equal to 1 over wavelength, right? It's equal to 1 over wavelength. So we can basically then say that wavelength is equal to H, or sorry, P is equal to H over wavelength. We'll relate it in terms of P. P is equal to H over wavelength, right? So interesting thing. What we basically said there is that momentum times the wavelength is equal to Planck's constant. So we're starting to see the the nuts and bolts where all this stuff is. These photons can be viewed as having a certain amount of energy. Their energy, they can be viewed as having a certain amount of momentum. That the momentum times the wavelength will give you Planck's constant, which is an interesting thing. There's a few things that happen because of this. If you've got a photon coming along, it's an electron. The electron gets knocked off over there, right? That's your little electron. Some of your momentum's gone through electron. That means your photon scattered this way. Now, depending on, we have this whole conservation of momentum thing. So depending on how the angle of the scattering, a certain amount of momentum will have been gained by the electron and lost by the photon. So the frequency of the photon is going to decrease, and how much depends on the angle of scattering. This whole thing, I think, is called Compton scattering. He did this with the X-rays and photons. But we need to basically be treating light or waves as point-like particles, and they've got an energy and they've got a momentum. Now, this next guy came along, de Broglie. We'll put this in here. And what he basically said, so we've looked at the momentum side, and basically he said, well, maybe we can treat the electron then as a wave. And so he said the little electron going around the hydrogen, we could think of that as a standing wave. And if we think of a standing wave, maybe only certain wavelengths can fit. And so he basically said, well, n wavelengths must equal 2 pi r. And which is interesting. But we already have this wavelength thing that we just derived, which says that wavelength is equal to h over momentum, right? So we can say n h's over momentum equals 2 pi r, right? And where's that going to get us to? Well, we can actually then say that P is equal to mv. So we could say that's equal to nh over mv, right? And if we bring the 2 pi down, what we're saying, we'll bring the 2 pi down here. So this is all looking good at this stage, right? And we can say, let's say we're trying to get to Bohr's theory, which was just MBR. So we put the MV up there. MVR equals NH over 2 pi. And remember, h over 2 pi was the same as h pi slash. So what you've basically said, de Broglie just came along and viewed this as a standing wave. And he ended up with Bohr's idea that angular momentum is quantized. So it's all starting to fit together, this whole thing between electrons being point particles, but really behaving like waves, and waves being quantized and seeming to behave like particles with a certain amount of energy and momentum. So we went from de Broglie saying this is a standing wave and just how many can you fit in there, and we ended up coming straight back to the quantization of angular momentum, which was cool. And so if you work backwards with this from the radius and velocity that we did before when we were working out the energies for the ground state of hydrogen, we just end up again back where we started from. Or you can look at, that's using the acceleration of an electron going around in a circle. We could accelerate an electron and do the same thing and find out what its wavelength is. So it's all pretty cool. All right, that's all I'm doing on that one.